Okay, thank you very much. It is my honor and pleasure to be here. To honor Maxim, who has been a great example for me in mathematics all my life. And I will talk about my joint work with Varchenko, which we did at the end of last year, and it's summarized in these two papers. In these papers, we introduced a notion of periodic pencil of flat connections. And this is a kind of generalization of connections that we know and love in representation theory, such as Knizhnik-Zamolodchikov connection, Casimir connection, Dunkl connection. And we discovered that there is a general setting, general definition, periodic pencil, which is both general enough to include basically all the examples we care about, and also we can it has really nice properties, so we can prove really rather strong statements about it. So X is going to be a smooth variety over some algebraically closed field, and in most examples it will be just an open set in affine space, so nothing complicated. And V is going to be a vector bundle on X. And in fact, I will consider only trivial bundles because, again, you lose nothing in this theory by passing to an open subset of X. So the bundle will be trivialized. Well, so then here is a definition. A polynomial family of flat connections on X with fiber V will be a family of flat connections. Well, since it's in a trivial bundle, it has the form D minus B, where B is a one form on X with coefficients in the endomorphisms of V, and it should polynomially depend on S1 through Sn.
No, for flat connection should divide by 2.
Okay, it depends on the definition of the bracket.
No.
Okay.
It is not described.
Okay, so so this means that we have this Maurer-Cartan equation, and then such a family will be called a pencil if it is the dependence on S is linear, homogeneous. So the flatness conditions are therefore the following. So we have, since this dB equal to 1/2 of BB should be satisfied for every S, this means that dBi equals to 0 and commutator of Bi with Bj equals to 0. But of course, if we are on a one-dimensional base, then these conditions are empty because these are two forms on X. But even the one-dimensional case for this theory will turn out to be interesting. So now another definition is that a family is periodic if there exist shift operators. So this is really the main definition. So it's periodic if there are shift operators, and shift operators should be matrices, invertible matrices with regular on X and with rational coefficients in S, which conjugate the connection nabla of S into connection nabla of S plus Ej, where Ej is the standard basis vector. So this means that every parameter S can be shifted by one by means of conjugation. The corresponding D modules are isomorphic.
So don't you to have kind of like D module in X direction, different separations in
Exactly, yeah. That's a very good way of thinking about it, yeah.
Make Milling transform with D modules in both directions, yeah?
Yes, that's right.
Okay.
But you see, the problem is that this is going to have, not quite, because this is going to have poles with respect to S. So
it still will make a difference, some difference D module.
It is difference D module, but to make Milling transform, since if you have things like 1 over s, it will be like 1 over the derivative. So it's a bit tricky. Okay, so it turns out that these have remarkable properties, and at the same time, there are many interesting examples. So let me explain some theory of such pencils. And then the most interesting things will actually happen in positive characteristic, but let me start with complex numbers. So in complex numbers, I'm going to fix a base point. And so my variety is connected. And then I have a monodromy representation, rho, from fundamental group of x with respect to this base point to the general linear group. And this depends on s. This is an entire function of s. And then I will make a definition that family nabla of s, it's a polynomial family, has periodic monodromy if representation rho s is isomorphic to rho of s plus ej for almost all s in an appropriate sense. In fact, the precise sense in which it doesn't have to be almost all, I only need to assume it's true for large enough set of s, which technically is a set that is not contained in a countable union of proper analytic subsets of affine space. So, and here is a theorem, first theorem, that suppose I have a pencil nabla of S, which means it's linear in S, and suppose it has periodic monodromy, then it follows that its monodromy is defined over essentially a field of functions, rational functions of exponentials of S. Or more precisely, I can only prove that it is defined over some finite Galois extension of this field, but it is invariant with respect to the Galois group. And conversely, if monodromy is defined over this, then well, the pencil has periodic monodromy. So, of course, the second direction is trivial, but the forward direction. So let me explain what the proof is, just modulo some details. So we have a holomorphic monodromy map, so from Cn, which is space of parameters, to the space of representations. So home from pi1 to GLV modulo GLV. Well, this is not a variety, this is a stack. So we have to be careful, but let me skip this. There is since we're interested in things birationally, this turns out not to be a problem. So this map is periodic with period z to the n. And also, so this means that it descends to a holomorphic map from C star to the n to this representation space. And because this is a pencil, since coefficients of differential equation depend linearly on S, this means that monodromy matrices depend exponentially, at most exponentially on S. So they are entire functions of order 1. And so this means that when I view them as functions of the exponential variables, they are of polynomial growth at infinity. And so, but that implies that it is a regular algebraic map, because it has polynomial growth at infinity. And now I want to lift it to a map from C star to the n to the matrix representation, so not modular conjugation. Well, the theory of invariant theory only guarantees that I can do it over a finite cover. So I have to, so the theorem, Étale slice theorem says that I can do it when I take finite cover. In practice, I have never seen an example where I actually need this cover, but for the proof I need it. And I obtain a map, algebraic map from some finite cover of this to this matrix, space of matrix representations. and this proves this theorem. So, so now the next theorem says that if I have a family nabla of S with regular singularity, then being periodic in the sense that I define there are shift operators is equivalent to having periodic monodromy. And the proof is, well, again, one direction is trivial, but the converse direction, periodic monodromy, implies existence of shift operators, follows from Riemann-Hilbert correspondence. So because it has regular singularities, Riemann-Hilbert correspondence guarantees that for sufficiently generic S, I do have an isomorphism of the modules from nabla of S plus Ej to nabla of S. And then some argument which is basically abstract nonsense based on Chevalier elimination of quantifiers, which I will skip, implies that this is not only true pointwise, but it's true in the family in the sense that there is a shift operator that depends algebraically on S with possibly some poles.
So you'll need some argument to go from analytic to algebraic, because...
Not even from analytic, from pointwise to algebraic.
Pointwise, and then you probably can see that in some places it's locally analytic, but then you have to globalize it to rational functions.
In fact, I do not go through analytic. I use Chevalier elimination of quantifiers to immediately go to algebraic. And yes. And why is this theorem useful? Because actually these shift operators they often exist in examples, but they are very difficult to compute. For example, for Knizhnik-Zamolodchikov equation, the shift operator that shifts the Planck constant from h to h plus 1 exists, but it's difficult to calculate and prove that it exists. But on the other hand, checking that monodromy is periodic is usually easier, or there are more available results about it. So this theorem allows us to check that many examples, we do have many examples of periodic pencils. So let me go over these examples. And here we delve in the field of representation theory. So the first example, which was our motivation, is the Knizhnik-Zamolodchikov connections, which arise in Wiesu-Witten model of conformal field theory. So this equation corresponds to a simple Lie algebra G. And then I fix a Cartan subalgebra H. I have to fix some weights, lambda 1 through lambda r, for this Lie algebra, and an element of the root lattice, which is positive in the sense that it has positive coefficients with respect to simple roots. And I will denote by m lambda the Verma module for this Lie algebra with highest weight lambda. So this means I fixed a Borel containing H and the polarization. And then I look at the tensor product of these Verma modules and take a particular weight space, which is a distance beta from the highest weight. So it is easy to show that this space depends only on beta and not on these continuous parameters lambda. And the Knizhnik-Zamolodchikov connection is the connection on C to the R with poles on the diagonals, which has the following form. So d minus h bar, which is this one of the parameters, times the sum of omega ij over zi minus zj times dzi. And omega is a Casimir tensor, so it's an invariant element here. And so it is well known that this connection is flat. The corresponding differential equation is satisfied by conformal blocks of Wiesu-Witten conformal field theory. And it's a pencil. Well, it's clearly linear in h bar. But if you identify all spaces for all lambdas, so make use of the fact that the space is independent on lambda and write down the matrices, you will discover that they are linear. We also have parameters lambda, which are weights. And you will discover that it is linear in both h and h lambda I. So there are 1 plus r times rank of G parameters here. And the theorem is that this connection is periodic. It's a periodic pencil. And the proof is based on what I explained. So since it has regular singularities, which is obvious from the formula, we have first order poles here. And it's easy to control what happens at infinity. So it suffices to show that it has periodic monodromy. But this follows from the Drinfeld-Kohn theorem. So Drinfeld-Kohn theorem, it's a deep theorem, but well known from the 1980s. And it says that monodromy of Knizhnik-Zamolodchikov equations is given by R matrices for the quantum group UQ of G, where Q is the exponential of pi I h bar. Well, we don't have a 2 here, so this means that we have to scale parameters, but I will skip this very minor technical detail. In the non-simply laced case, there is another normalization, which is also totally unimportant. So this is a rational function of Q and Q to the lambda I. And this exactly means that it is periodic with respect to h bar. If I shift h bar by an integer, in this case twice an integer, or I shift lambda by times h bar by an integer, the monodromy won't change.
What is omega ij in the formula?
This means omega. Omega is an element of symmetric square of G invariance. So it's an inverse of the Cartan of the killing form, let's say. Yeah. And then we act by it in a, so see, we have a tensor product of R representations. So we can act by the first component in the i's factor and the second component in the j's factor. So it's okay. Now this has many generalizations. One can consider Knizhnik-Zamolodchikov equations for Kac-Moody algebra. So replace G with a symmetrizable Kac-Moody algebra, or we can consider Lie superalgebras, or we can consider trigonometric Knizhnik-Zamolodchikov equation or elliptic Knizhnik-Zamolodchikov equation, Knizhnik-Zamolodchikov in the Lie category, and others. So I will not go over these examples. One can talk about them. It could give a separate talk. I'll give another. So basically, there are 3 families of connections that arise in representation theory. So the second one is Casimir connections. So this was proposed by De Concini in mid-90s and studied a lot by Toledano Larreda. And this is the following. So we still have a simple Lie algebra. And then we have Cartan subalgebra. And we have regular part, which means we delete reflection hyperplanes. And we have Fermat module, M lambda. And we again take weight space of vectors which are at distance beta from the highest weight. Call this space V. Again, it's independent on continuous parameter lambda. And then we write Casimir connection with which is a connection on the bundle with fiber V, which is the following: D minus H bar. And here is a summation of the positive roots. So E alpha and F alpha are root elements of our Lie algebra. So you write this SL2 Casimir without the Cartan term, basically, or you can include Cartan term, it doesn't matter, times D alpha over alpha. And, well, it is known that this is flat. And it's a pencil with respect to parameters H bar and H bar lambda. So very similarly to the previous case. And the proposition is that this is a periodic pencil.
No, it has irregular singularities.
No, it has regular singularities. No, you can. There are these things do have deformations which have irregular singularities. And in fact, so what the periodic pencil says we will see always have regular singularities, but there is a sometimes you want to consider some irregular equations such as the quantum Toda system and so on. And those for those there is a generalization which is called mixed pencils. They are difference connection for some variables S and continuous differential connection with respect to other. And the theory extends to that case. But I won't have time to explain this. Okay, so this is periodic, and the proof is the same style as before. So it's a regular singularity, so it's enough to establish periodic monodromy. And luckily, this is already available in the literature, although later it was done in full generality only recently by Toledano, Lareda, and Appel. And they showed that monodromy of this connection is given by the quantum Weil group of uq of g, which depends on q and q to the lambda. So this was a many-year project by Valerio Toledano Lareda, and finally it was finished several years ago. And the generalization is, they also did the case of Katz-Moody algebra, so we can do it in that case. There is also trigonometric Casimir connection with values in the Youngians, and this case also is done, so also we get periodicity. And the third type of connections, they come from Coxeter groups, but let me explain it in the case of Weil group. They are called Dunkl connections. And in this case, you have W, which is a finite Weil group with reflection representation H again. And V is a representation of this group. And then the Dunkl connection is actually a very simple connection on the regular part of H, which means the complement of reflection hyperplanes. And it has only one parameter H bar. And it has the form D minus H times the summation of over reflections S of this group S times this logarithmic form D alpha S over alpha S, where this is the root corresponding to S. Alpha S is the root corresponding to S. So this is a flat pencil with parameter H bar, and the proposition is that it is periodic, and the proof has the same style, but in this case, actually it's much simpler. So we know that that it's regular singularity, so it has periodic monodromy, but then monodromy is a representation of the Hecke algebra, HQ, where Q is e to the 2 pi I H. This is very easy to see because quadratic relations of Hecke algebra are implied by the local analysis near the reflection hyperplane. And this Hecke algebra is okay, and so this is a finite dimensional semi-simple algebra for generic Q, and this implies that representations, if you know basically the Q, then representation is completely determined, so it's periodic. And this has many generalizations also, complex reflection groups, trigonometric Dunkl connections for Weil groups, which were considered by Cherednik and Heckman, and so on.
You have a 2 here, unlike this.
Yeah, there is a 2 here, yes. There is a 2 in this case, but this is totally unimportant. It's a question of normalizing parameters. And then the last example is a kind of geometric, which contains many of the previous examples. So it comes from the enumerative geometry. So in this case, let me consider conical symplectic resolution of singularities. And suppose it has a torus action. So there is a dilation and also maybe some other torus. So we have a torus action, and suppose it has finitely many fixed points on the y tilde. And so in this case, well, we can consider the equivariant quantum connection. Maybe I should say equivariant. So this is a connection which, well, initially it is formally, it's defined formally, but you know, let's assume it's not known that it converges, but let's assume that it does in our case. So then it will be a connection which with base second cohomology of y tilde with C star coefficients without some divisor of singularities, and the fiber is the total cohomology. So this is a flat family which depends on parameters S1 through Sn, which are equivariant parameters of the torus. As was explained to me by J. He, if we have this condition of finitely many fixed points, then in some basis, which is called the stable basis, this connection form will depend linearly on S. And so the proposition is that this is a periodic pencil. And in this case, actually, you don't need to worry about monodromy because in this situation, in the work of Okounkov, Panharipande, Malek, Braverman, and others, it is shown that these shift operators exist, and namely they come from geometry. They are obtained from so-called stable envelopes. Okay, so let me explain now why. So I explained that there are many interesting examples of these periodic pencils. Let me now explain why we care, why we wanted to separate this class of differential equations. And the first thing is these periodic pencils have the property that their singularities are strongly constrained. They occur, more precisely, they occur in on hyperplanes defined over Q inside the space of S parameters. So I said that things can have poles with respect to S, and it turns out that if you have a periodic pencil, then the poles are restricted to these hyperplanes. Well, I can only prove it up to shift, which means that the equation of the hyperplane has rational coefficients of the linear terms of the variables, but the constant term I cannot show that it is rational, but in all examples it is. So that's a pretty surprising property. So let me give an example of precise theorem or to that extent. So, let me, for example, take the non-isomorphism locus. So I said that we have this periodic structure, which means that the module nabla of S is isomorphic to nabla of S plus Ej. But this happens not for all S, but for most S. So there are some S for which it is not true. And let me call this set Bj. Well, it's not the risky closed in general, so let me take the closure. And then it contains this is contained in the pole divisor of the shift operator Aj with respect to S. And here is a theorem that every codimension 1 irreducible component of this Bj bar is a hyperplane defined over Q up to shift. And moreover, if nabla of S is generically irreducible, which is true in many examples, then the poles of Aj, regarded as a projective linear transformation, so modular scalars, occur on such hyperplanes. So poles of the shift operators, when we kill the scalar, also restricted to hyperplanes defined over Q. And similar results can be proved for other types of singular behavior of nabla of S. For example, we might be interested in the non-semi-simplicity loci. So points, suppose it is generically semi-simple for generic S, then we might be interested in the set of all S when it is not semi-simple. And it's going to be the same. Or jumping loci of endomorphism algebras of the D module, and so on.
Linear dependence on S is important.
Yeah, well, I mean, it's important in some aspects. Not at this point, not very important. In characteristic P, it will become more important. So, so I will explain how this is proved, but for this, one uses the following theorem, which is interesting in its own right, and which says that every periodic pencil is regular, has regular singularities with respect to the x variables. And this in particular implies the following fact about enumerative geometry, that if you have this quantum connection for some variety, and it turned out to be convergent and have rational coefficients, then it will have, so if it's on a symplectic resolution with finitely many fixed points, it will be regular. So it's something that people in symplectic geometry don't know how to do. They only know how to prove such things after they have already computed the connection in a particular example. And this is actually proved using characteristic P. So I will explain this in a few minutes when I pass to characteristic P. But now I'm going to use this to prove that singularities are restricted to hyperplanes. And this can be done using another theorem, which is actually rather simple and pretty old. And it's a special case, simple special case of a theorem of James X, which was one of the kind of early results in what later became model theory. So, and it's a very simple statement, which actually has an elementary proof, which I wrote down, but then I discovered that it was a special case of this theorem. Suppose you have an irreducible algebraic hypersurface in Cn, such that exponential of this hypersurface in C star to the n is also contained in an algebraic hypersurface. Then Y is a hyperplane defined over Q up to shift. So that's a very nice and rather simple theorem. So it's, maybe it should be an exercise. So it's really not difficult. But the proof of restriction of singularities to hyperplanes is then the following: that by the regularity theorem, which I haven't yet explained, and Riemann-Hilbert correspondence. So by regularity theorem, nabla is regular, and by Riemann-Hilbert correspondence, the non-isomorphism of nabla of S plus Ej to nabla of S is equivalent to non-isomorphism of monodromy representations. Because Riemann-Hilbert correspondence says that flat connections with regular singularities and representations of fundamental groups are equivalent categories. But rho S, by the first theorem I explained, is defined over functions, rational functions of the exponential variables, or rather over some finite extension of it. Which means that if I take exponential of these sets Bj bar, where we have non-isomorphism, this is contained in a certain algebraic hypersurface in C star to the n. So Bj bar is contained in an algebraic hypersurface, and exponential of Bj bar is contained in algebraic hypersurface. So this means that every coordination 1 component of this thing is a hyperplane defined over Q up to shift by this X theorem. And I should say that this actually, for me, shed some light on why I've been doing representation theory for many years. And in representation theory, there are usually some parameters, and representations behave in a certain generic way for generic parameters. And then for special parameters, something happens. They become reducible. They, simple modules become smaller, and so on. And always, at least in representations of things from the Kac-Moody world, it always happens on hyperplanes with respect to parameters.
Yeah, but actually I have to say that all varieties on which connections also complements to hyperplanes, like Knizhnik-Zamolodchikov equations, numbers not equal to each other.
Exactly, and that's because there is a duality. So actually, there is a duality. So Knizhnik-Zamolodchikov equations are dual to these Casimir equations, for which the z variables become parameters and the lambda variables become variables. So things happen on hyperplanes, and I was wondering, why is this so? And while doing this, I get a clue that this is because in many cases kind of representation theoretic structures are encoded by these periodic pencils.
Question. Do you have in all your cases some holonomic dimensional product of your variety times torus, and then multiply by fractional powers and take direct image? That will explain everything.
So this is you're asking if this is if these connections are geometric, if they come from some sort of Hodge theory.
No. You have some holonomic demodel product of your variety times torus with number of parameters. Yeah, and then you multiply these things by fractional powers. You take direct image, and then it will be automatically things which, like in the Raman realization, depends polynomial on parameters, and in periodic in Betti realization.
I have to think about it, but
this explanation what is going on. It's a bit similar to what you missed on the first talk by Takuro Mochizuki. There are scalable demodels that when you have, like, for exponential integrals, not for fractional powers, the same behavior.
Yes, it's possible. Like I said, there are poles with respect to S, so I'm a little worried about that. But
yeah, then it automatically appears in hyperplane rational compensation framework. Yeah.
So is the locus purely of codimension 1, or you don't know?
Yeah, well, I cannot deal with higher codimension things. Probably, I mean, in all examples, all you have is a codimension 1. There is no components of smaller codimension, but so there are just intersections of hyperplanes. But I don't know how to prove that. Okay, so now I want to consider connections and positive characteristic. And so here I have to recall the notion of p-curvature. So, so in characteristic 0, if you have a flat connection, which means it has 0 curvature, then it has a full set of formal flat sections near every point. However, this is not true in characteristic P, as the simplest example shows. If you take the differential equation for the exponential function, dy over dt equals to y, then this has no non-zero formal solutions near 0 in characteristic P, because if you write the formal series, the only one that could be a solution, it's the exponential series. It is defined only in characteristic 0 because it has these denominators n factorial. And that's because connections in characteristic P actually have another kind of curvature, which also exists in dimension 1, and which is called the p-curvature. It's very easy to define. Suppose we have a connection with covariant derivatives nabla I with respect to some local coordinates xi. Then p-curvature is the collection of operators ci, which is nabla I to the p, which of course commute because nabla I do. And the important fact is that these operators do not have any derivatives in them. So they belong just to k of x times endomorphisms of v without any derivatives. And for example, in the above equation, we have d minus 1. Nabla is d minus 1. So c is nabla to the p, which is d minus 1 to the power p, which is d to the p minus 1. And this is just minus 1 because d to the p acts by 0 on functions in characteristic p. And so if you have a formal flat section, so now why is it that this p-curvature is obstruction to existence of flat sections, or having a full set of flat sections? Well, because if you have nabla I times f equals to 0 equation for a flat section, I can multiply it by nabla I to the p minus 1 and get equation nabla I to the p times f equals to 0, which is the same as to say that ci times f equals to 0. But ci are just matrices over functions on x. So in order to have a full set of solutions, these matrices have to vanish. And more generally, if we have a generic point x on x, then we can compute the dimension of the space of formal solutions. So formal solutions form a module over what plays the role of constants in this theory, functions with 0 derivatives, which are formal power series in piece powers of the variables. And then the statement is that this module is free with dimension equal to the dimension of the common kernel of the matrices Ci of x. And it has algebraic basis. So actually, in characteristic P, all differential equations have algebraic solutions. So that's not a problem if they have solutions. OK, and here is the next theorem. So this is maybe the main one. This is maybe the main reason why we were interested in periodic pencils, because this notion allows us to compute something about the p-curvature of these pencils. So suppose you have nabla of S, which is D minus some Sj Bj. So this is a periodic pencil. And then the claim is that the p-curvature operators, Ci, are isospectral to the following expression. So we take Bj are our terms in this connection, coefficients of Sj. So they are one forms. So I can write them as the sum of Bij times dxi. Then these are just matrices, matrix functions. So I can take their Frobenius twist, which means I raise every element to power p. And then I sum them with coefficients, but Sj is transformed by the Artin-Schreier map, Sj minus Sj to the p. And I take this sum, and then this is the isospectral, which means they have the same eigenvalues, joint eigenvalues, with the same multiplicities. So in particular, if they are regular semi-simple, this would imply that they are conjugate. So this is a rather striking fact, because in general, for general differential equations, we can say very little about the p-curvature for arbitrarily large p. So of course, for every fixed p, this is just a finite computation, but the complexity grows with p. We get some non-commutative differential polynomials of the matrix, and this becomes a big mess. And there is no coherent behavior for different p's. But here we have a totally different picture. And for the proof, let me explain the proof, which is actually quite short and simple. For simplicity, I will assume that my base is one-dimensional, and I only have one parameter. Nothing changes if you pass to the general case. The idea is the same. And the details also are almost the same. So let C of S be the p-curvature of nabla. So this is just a single matrix depending on S rationally. Actually, regularly. It's a polynomial of S with values in matrices. And we know that our pencil is periodic. Nabla of S plus 1 is isomorphic to nabla of S. And this means that C of S plus 1 is conjugate to C of S as a rational function. Which means that if I look at the coefficients of characteristic polynomial of C of S, then they are periodic in S. On the other hand, I can control the degree, because C of S is nabla of S to the p, and nabla of S is linear in S. So this is the main place where we use linearity with respect to S. And this is unfortunate because actually we want to extend this theory to the Q difference equations, in which case the linearity in S is lost, and this step fails. And but all the statements, all the theory should extend somehow. So this is one of the problems. But in this case, we do have a degree bound. So Bi of S is a polynomial of S of degree p times I. Because C of S is a polynomial of degree p. And this means that, well, we know that it's periodic in S, and that it is polynomial of degree pi. But because it's periodic, it's a polynomial of S minus S to the p. So any polynomial in characteristic p, which is invariant under shift by 1, is a polynomial of S minus S to the p. And this polynomial beta I has to be of degree I. But also we have C of 0 equal to 0, because at 0 our pencil is linear homogeneous in S. So for S equals 0 we just get the trivial connection which has 0 p-curvature. So this means that the matrix C of S is divisible by S. And this means that its coefficients of characteristic polynomial are divisible by S to the I, because they are sums of minors of size I of a matrix whose every entry is divisible by S. And well, this means, so we have a polynomial like this, where beta is a polynomial of degree I, and it is divisible by S to the I. Well, that means that this polynomial is just a monomial, which is a constant times u to the I. And then it remains to compute this leading coefficient. And the leading coefficient is computed by WKB approximation, where we send our S to infinity. Well, then, well, I mean, you have d minus sb to the p, and it's clear that the leading term there will, which is of power s to the p, will be minus b to the p. And b to the p, its characteristic, its eigenvalues are the same as the Frobenius twist of b. So, so beta 0 I is equal to the coefficients of characteristic polynomial of the Frobenius twist of b. And this two matrices are isospectral if and only if they have the same characteristic polynomial. And so we obtain that our p-curvature C of S is isospectral to S minus S to the p times b1. So it's a very simple and elementary proof. So a corollary of this, which is nice, is that if I specialize periodic pencil to, so now we're talking about pencils in characteristic P. So if I specialize it to Si in Fp, then its p-curvature is nilpotent, because it's isospectral to 0. So this, if S is in Fp, then S minus S to the p is 0. So the previous theorem says that it's isospectral to 0, which means it's nilpotent. And so in particular, this is true. This gives us so this gives us information. This main theorem gives us information about the p-curvature of connections in all these representation theory examples, KZ, Casimir, Dunkl, quantum connections, because we can reduce them to characteristic P for large enough P. So it gives us information about their p-curvature. And in this connection, I should recall a theory of Nick Katz from a long time ago, where he introduced the following important definition, that a connection defined over, flat connection defined over Q bar is globally nilpotent if its reduction to characteristic P has nilpotent p-curvature for almost all P. And so a theorem, therefore, is the following, that a periodic pencil defined over Q bar, evaluated at rational values of S, is always globally nilpotent. So it follows from our argument. And the reason this global nilpotence is interesting is, for example, because there is a theorem of Katz, not so hard, which says that any globally nilpotent connection has regular singularities. So this in particular implies what I claimed in the first half of the talk, that every pencil, periodic pencil, has regular singularities. So this follows from the theorem that it is globally nilpotent, and that theorem of Katz that globally nilpotent connection has regular singularities. And so here I should make the following remark, that so Katz proved that if a connection nabla over Q bar is geometric, which means it comes from Hodge theory, or more precisely, it means that it's semi-simple and its irreducible constituents are direct sums of Gauss-Manning connections of families of smooth projective varieties, then nabla is globally nilpotent. And but the converse is a conjecture, actually a very ambitious conjecture, by Andrea Bombieri and Dwork. And it generalizes Grothendieck-Katz conjecture, which says that nabla has zero p-curvature upon reduction to almost all primes, if and only if it has finite monodromy representation, which means an algebraic fundamental solution. So both conjectures are wide open. In fact, the Andrea Bombieri Dwork conjecture, I'm not even sure if everybody believes it, but the fact is that people tried to find counterexamples, so they constructed various examples, and then later people were able to produce geometrically those examples. So far, the project of finding counterexample has not succeeded. However, so I don't know if all periodic pencils are geometric. So many of them are. The Knizhnik-Zamolodchikov connection is geometric due to work of Shechtman and Varchenko. Casimir connection is geometric through work of Felder, Varchenko, and co-authors. But for some of them, it is unknown despite many efforts. For example, for Dunkl connections for exceptional Coxeter groups of type E6, E7, and E8, this has been an open problem for 30 years. Nobody has been able to produce a geometric construction. And so we get a lot of explicit examples of connections which pass all tests of this Andrea Bombieri Dwork conjecture that are accessible, such as global nilpotence, for example, but for which we don't know a geometric construction. And maybe the last little topic, we can introduce the following definition, which is a poor man's version of the notion of a geometric connection, because it's much simpler, although it's not quite what we want. So a regular flat connection nabla defined over Q bar is called quasi-geometric if its monodromy representation is also defined over Q bar. So the pencils of my examples evaluated at rational points are therefore quasi-geometric. And this is, of course, a rare property because monodromy is a transcendental procedure, so it's very unlikely to map algebraic numbers to algebraic numbers. But on the other hand, every geometric connection is quasi-geometric because, first of all, well, it's defined over Q bar, and monodromy, well, if you have a family of projective varieties, monodromy representation can be computed topologically, so with cohomology with rational coefficients, which means that if you have a semi-simple situation, direct summands are defined over Q bar. And here is, so in Hodge theory, there is one of the most basic theorems says that if you have a geometric connection, then its monodromies around divisors and any compactification of the base are quasi-unipotent, which means that some power is unipotent. Eigenvalues are roots of unity. And the same holds for quasi-geometric connections. And the proof actually, there is a proof of this monodromy theorem in Hodge theory due to Brieskorn, which can be extended verbatim to the quasi-geometric setting. It's a very remarkable proof, which I didn't, to my shame, didn't know about, but it's contained in Deline's book on the regular differential equations. And the proof is the following. So if you haven't seen this before, you will enjoy it. So one of the most beautiful things I have seen, maybe. If lambda is an eigenvalue of the residue of the connection at a codimension 1 component of x bar minus x in some trivialization, where you have first order pole, then e to the 2 pi I lambda is the eigenvalue of monodromy. And if nabla is quasi-geometric, then both of them have to be algebraic numbers. But then we can use the theorem of Genfond and Schneider in transcendental number theory, which says that if you have a number lambda such that it is algebraic and its e to the 2 pi I lambda is algebraic, then it is a rational number. And exponential is a root of unity. Okay, and so then maybe the last thing is this is a bit off topic, but actually these quasi-geometric connections arise in the conformal field theory and the theory of fusion categories. So, so suppose we have C, which is a braided fusion category over complex numbers, and so then we have this. So we have representations of braid groups and mapping class groups attached to this category, and by Riemann-Hilbert correspondence, they define flat connections with regular singularities on configuration spaces of points on curves on P1. Well, in the modular, if the category is modular on all genera, if category is just braided, in genus 0. And the claim, the conjecture is that they are all quasi-geometric. Well, it is hard to do directly because in reverse, well, Riemann-Hilbert correspondent forward is analytic continuation, so it's transcendental procedure, which is doable, but the reverse map is transcendental and undoable. You don't know how to compute it. And so, but nevertheless, there is this conjecture, and here is a case when you can prove this. Suppose C is a representation category of a vertex algebra, which is strongly rational. So it's a kind of precise version of notion of rational vertex algebra, which means it has semi-simple representation category. All such vertex algebras that are known are defined over algebraic numbers, but it's not proved, so I'm going to assume this. And then this conjecture holds. So we get quasi-geometric connections. And the proof is that in this case, this connection is the Knizhnik-Zamolodchikov connection for this vertex algebra. So because it's an algebraic procedure, it is defined over the same field, Q bar. But monodromy is a braid group representation of fusion category. And in that case, fusion categories are all defined over Q bar by a theorem which is called Ockniano rigidity. So this was proved for unitary category by Ockniano, and for general category in my paper with Nikšić and Ostrik many years ago. So since it is, because the deformational cohomology of such categories vanishes, and in this situation, general nonsense implies that they are defined over Q bar. So we obtain a quasi-geometric connection. And I was hoping that this can actually be turned into a proof in general, because braided fusion categories can be defined in the de Rham world using Teichmüller towers. So this is a famous Deligne letter to Drinfeld, which is explained in the book of Bakalov and Kirillov. And if we can establish Ockniano rigidity in that setting, we would get algebraicity of this local system both in de Rham and Betti world. But I couldn't push it through. There is a young man in this room, Pierre Godefroy, who it's a proof in progress along these lines of this conjecture. So hopefully it will be finished. Thank you very much.
Yes, professor, do you require that the shift operator satisfy the cocycle condition? If you shift.
Actually, I didn't require it. Of course, in all applications they do, but I didn't need it for the proof.
No, but I think at the end of the day, if you make Milling transform, you get like geometric demodeling product before writing the torus, and that's explained.
Well, maybe I have to think about it. I don't know how to make this. For example, how to make Milling transform. Suppose you have KZ equation and you want to make Milling transform with respect to H bar. Let's say we have finite dimensional representations, SL2, and we have H bar, which is just the only parameter. How do you make Milling transform with respect to H bar? So it's, I mean, yeah. So it's not so simple because you have poles with respect to H bar. So it's a non-trivial business. So I actually, it would be extremely, for example, these shift operators, if we can calculate them, that would be extremely interesting. Even in the case of SL2. I mean, if we can effectively calculate them.
Go ahead.
Yeah, I'm just wondering if what you're saying also applies to, you know, the Toshio-Yamada connection, which is a higher genus analog of this.
Yes, yes. This will all be, if this is done by Pierre Godefroy, this will also include that.
But there we know that the monodromy is not finite.
Yeah, it doesn't need to be finite. It just needs to, but matrices in some bases should be algebraic.
But you had something, maybe I did not quite understand, but you had something about finite monodromy.
No, there was there's Grothendieck-Katz conjecture, which I mentioned only for the purposes of motivation. It had nothing to do with the subject matter. And in that case, it is finite.
Because we know they're not finite.
Yeah. This is a more general class of connections with, so actually, it is not known if all these connections are actually geometric. Because it is very difficult, if I give you a connection, it is very difficult to prove that it is geometric, and it is even more difficult to prove that it is not geometric if it passes all the tests that we know, such as nilpotency of p-curvature. So some connections we know how to prove they are not geometric, such as, for example, Lemay equation for generic values of parameters are not geometric because it is known that their p-curvature is not nilpotent. But if p-curvature is nilpotent, then you are stuck. And so, in fact, it is entirely possible that in another 10 years, somebody will come up with a construction of the geometric model for the Dunkl connection. So it would be extremely interesting. But we cannot rule out this possibility.
More questions?
Can I have, do you have an application for conjecture, no, for theorem for 2? Use the Gelfand-Schneider theorem.
No, I don't have application. No, it's but it's a nice thing to know that. For example, it might vertex algebras, rational vertex algebras. Well, definitely all examples we know are defined over Q bar, but actually. I have not even seen an example where you need irrational numbers. That somehow, if you have I do know an example of rational vertex algebra where you have to use square root of 2 or something like that.
Actually, you know, Dunkl operators have meaning in topological quantum field theory. In the sense geometric, in a sense.
It's different.
Well, what do you mean by geometric?
No, geometric means it comes from Hodge theory, that this is a connection on cohomology of something.
No,
but it sort of charges the appearance of irrational quadratic rationality in some CD stuff. You get some really bizarre.
No, well, no. Okay, so
it should be rational and normal not.
No, the dimensions could have square roots of 5 and things like that. But that's on the Betti side. On the de Rham side, on the Betti side, we will get exponentials of these rational numbers. So the roots of everything is cyclotomic, always in all examples.
Okay. Anybody else?
So quasi-unipotency of monodromy may have to do with the fact, may explain the fact why somehow, well, I mean, it's a small manifestation of why we always get, in the topological theory, we always get cyclotomic fields.
Okay, there's no more questions, so let's end.